live stream, and then we can get started.
You asked if he's okay.
Yes, I always ask.
Okay.
Sense is important.
Especially with MoTe stuff. Don't know.
Yeah, I don't know if we're gonna hear about published work or not, but anyway, yeah, okay. Great. So today we're happy to have Aidan Reddy from MIT in our seminar. He got his undergrad in Columbia, and right now he's working at MIT with Liang Fu. His research focuses on collective behaviors of strongly interacting electrons in two-dimensional materials. And today he's going to tell us about some cool new stuff in twisted MoTe2.
Thank you. Thanks for the nice introduction, and thanks to Omri for inviting me and for the opportunity to share my work today. And thank you all for coming, of course. I'm using my headphones right now, and as we were setting up, it seemed like the audio was going in and out. So if you guys can't hear me at any point, just send a message or something, but hopefully it won't be an issue. Yeah, so today I'm going to be, talking about two works that are listed here. The first one is called Non-Abelian Fractionalization and Topological Minibands that was published in PRL this past fall. And the second is a more recent work on arXiv now called Anti-topological crystal and non-abelian liquid and twisted semiconductor bilayers, which is kind of a follow-up to study the phase diagram in the second miniband of twisted MoTe2. So these works were done with Nisharga, Ahmed, Emil, Donna, and my advisor, Leon.
The title's very negative.
Very negative?
Yeah, anti, non.
Oh. Yeah, I guess now that you say that, yeah. I was scared for a moment. I thought you meant negative in another way. Yeah. But that is true. That is true. Okay. So yeah, I'm going to begin just with a bit of an introduction to fractional quantum anomalous Hall effect in twisted MoTe2 and how we can think about the electronic structure in the system. So sort of the paradigmatic example of strongly correlated topological electronic phases is the fractional quantum Hall effect, which was originally discovered in two-dimensional electron gases subjected to a large magnetic field. And one of the reasons why these gapped electronic states are interesting is because they have as their elementary excitations quasi-particles with fractional charge and fractional exchange statistics. So we call this fractionalization and topological order. They also have a quantized Hall response. And it was realized initially around 2011 or so that if you take a Chern band and put particles in it, fermions or bosons, and add some interactions, you can realize a very similar many-body ground state to what you get in Landau levels. These go by the name of fractional Chern insulators, or in the more specific case where there's no external magnetic field, the fractional quantum anomalous Hall effect. And so this is a way to realize these interesting phenomena of fractionalization and topological order in a new setting, a very different microscopic setting that could potentially lead to, for example, this effect happening at higher temperatures, because the characteristic energy scale is now set by the Coulomb interaction at the lattice scale rather than the magnetic length. So I'm going to skip a lot of important experimental developments that came along the way, but basically it turns out that the best way that we have had to realize this effect so far, and the one that has proven successful, is to use MoRe materials. So in the spring of 2023, there were some breakthrough results from Xiaodong Xu's group where they measured photoluminescence associated with tryons in this twisted MoTe2 semiconductor MoRe system. And they showed basically that when you have a state that has an electronic state that's incompressible, that results in a lower photoluminescence associated with these tryons. So that's just dark purple on this plot. So then they changed density and magnetic field and measured this photoluminescence, and you see that these kind of dark purple features are occurring these incompressible states are occurring at a density that depends on a magnetic field. And whenever you have an incompressible state that occurs at a density that depends on a magnetic field, that's a quantum Hall effect. And when they occur with fractional slope and at a fractional filling of a band or Landau level system, then that tells you that interactions have to be responsible for opening that energy gap, and has to be topological order. So this provided very strong initial evidence for the existence of fractional quantum anomalous Hall states in the system. These lines go all the way down to zero field. Then coming from Cornell, a group of G. Shan and Kin-Fai Mak, they did thermodynamic measurements on the system, measurements of the electronic compressibility, and they basically, the reasoning through the data is the same thing. There's a Landau fan. And later, just a few months later, direct transport measurements on the system showed the existence of anomalous Hall plateau. In particular, this is at fillings 2/3 and 3/5 of a hole per Moiré unit cell are the most robust fractional states that have been seen so far. And since then, there's been a number of other experimental works using different probes to show the existence of these states. So how should we think about why you get fractional quantum Hall type effects in this system? The first question you should ask is how to think about the electronic structure of holes that we dope into this Moiré system. So just to remind you, this is a so-called K-valley TMD homobilayer. So we have two layers of molybdenum ditelluride, in this case, MoTe2, and their low energy holes live in the K-valleys, and we stack them so they're crystallographically aligned, and then we give them a small twist. So the low energy holes live in the valleys K and K prime, and to a good approximation, that valley number, which is locked to spin due to strong spin orbit coupling at the valence band edge, is a good quantum number. So we can write a valley projected Hamiltonian that I'm just calling H here, that describes the low energy electronic structure of holes in this system. So you have a quadratic energy just coming from the valence band edge curvature. And the way that the Moiré enters is to produce this so-called layer Zeeman field that I've written as J of R here in red, that couples to a layer pseudospin. Spin up is top layer, spin down is bottom layer. And it also creates a scalar potential. And so in this plot, that's showing this layer Zeeman field. The colors here correspond to the Z components of J, which physically mean a position-dependent interlayer electrostatic potential difference. And the in-plane components, the XY components of J of R, are the real and imaginary parts of the local interlayer tunneling amplitude. And so if you try to calculate within a given Moiré unit cell, does this layer Zeeman field, what is it doing? Does it wrap around the layer block sphere? You can calculate a number called the wrapping number just to integrate the wrapping density. And you find that that number is non-zero. And so what that actually tells you is that there's a skyrmion in every Moiré unit cell in this layer Zeeman field. So it's a skyrmion crystal. So this layer Zeeman field has this topological property in real space. And so what does that mean for the electronic structure? So one way to kind of make progress on that question is to make an approximation called the adiabatic approximation, or that's what we'll refer to it as. And so what you do is you assume that the layer Zeeman field is the largest energy scale of the problem. And this may be more or less quantitatively accurate or inaccurate, depending on what twist angle you're at, for instance. But when the layer Zeeman field is the largest energy scale, then that means that all the low energy holes are going to want to align their layer pseudospin at every point in real space with the layer Zeeman field. So you can project onto hole states that satisfy that property. And when you do that, you've now projected out this layer pseudospin. So you end up with a Hamiltonian that doesn't have any layer pseudospin degree of freedom. But actually what you've picked up is an emergent vector potential, A of R, that has an associated emergent magnetic field. And the way to think about this emergent magnetic field is that, okay, so you you had these holes moving around that were forced everywhere they are in real space to align with J of R. And now that means that with every path in real space that a hole takes, there's an associated path on the layer block sphere that in general will enclose some solid angles. So you know that there's a Berry phase associated with closed loops that enclose a non-zero solid angle on the block sphere, and you can reformulate that in terms of an Aharonov-Bohm phase associated with the closed loop in real space enclosing some magnetic flux. So that's how the emergent magnetic field comes in. It's associated with the Berry phase from the layer block sphere. And it turns out that if you ask what is the net magnetic flux of this emergent magnetic field per Moire unit cell, the answer that you get is precisely, in units of the magnetic flux quantum, the answer that you get is precisely this Winding number. So because that was, or at least the absolute value of that was 1, that tells us that there's a net flux per Moire unit cell of 1 flux quantum. And by the way, please feel free to interrupt at any point and ask questions. Okay, so what does this emergent magnetic field look like? Well, it's actually highly non-uniform and fluctuates very strongly. So this is the emergent magnetic field on the left-hand side. You can see it varies a lot. And most of the magnetic flux is kind of concentrated on this Kagome lattice almost of these red points. So the Hamiltonian, one way to think about it is take the part of the Hamiltonian that's just the uniform magnetic field and then call everything else fluctuations, and maybe they're not small. But yeah, they're not small, as you can see from these plots. So it's not a priori obvious whether or not the electronic structure that you'll get out is going to look like Landau levels, or if the fluctuations are going to really profoundly change things, like for instance cause band inversions. So the answer to that question of whether or not the bands look like Landau levels depends on the twist angle. And there's basically, for our purposes, there are kind of 2 regimes. So one regime is at small twist angle, when the kinetic energy of the holes is very small. And what happens then is that the holes get tightly bound to the minima of this effective scalar potential, V tilde of R, which if you look at this plot, you see that those minima form a honeycomb lattice, these dark blue regions. So in that regime, the holes get tightly bound to those minima. And so now you have a tight bonding model on a honeycomb lattice, and there's broken time reversal symmetry. So you get basically a Haldane model out in terms of these first 2 whole mini bands up here. And they also have an opposite Chern number, which of course has to be the case in just a 2-band model. But then when you go to larger twist angle, you actually enter a regime where things look more like Landau levels in the following sense. There's a particular twist angle at which the second and third mini bands invert. And across that band inversion, the second mini band, the lower one on this plot, so up here in these plots, the semiconductor band gap is up here. And the second mini band goes from having opposite sign Chern number to same sign Chern number as the first mini band. So in this sense, it's what I'll call the Landau level regime, because if you had Landau levels, you would have a bunch of mini bands with the same Chern number. So at least the first 2 having the same Chern number is more like Landau levels than the opposite case. So this will be important, the existence of this band inversion later.
Question?
Yeah.
I haven't been following all this until this moment. You've made this all very clear to me for the first time.
Cool.
So, but there was a very important missing point that I kind of blinked.
Yeah.
So somehow time reversal symmetry was broken somewhere at some point, I guess.
Yes. Yes.
And that's supposed to be spontaneous, or like it kind of happened fast. Maybe everybody else knows this except me.
Yeah. So that's a good question. So this H, if I wanted to be more careful, I should have put a subscript K here to indicate that this is
so this is for a given valley.
Yeah, this is for a given valley. And in the other valley, the layer Zeeman field, the other valley, H of K prime would just be the time reversal conjugate of this.
So then the experiment seeing the signal is supposed to be like spontaneous value polarization or something? Is that the
Yes,
picture?
yes. So there is spontaneous valley polarization in experiment. And there's, I mean, the existence of time reversal symmetry breaking is established by MCD. They measure magnetic circular dichroism, which I didn't show plots of. And the fact that you get a non-zero signal there is telling you at the very least that the time reversal symmetry is broken.
And do they occur like in sequence or all at once?
In terms of density,
In terms of, I don't know, in terms of whatever tuning parameter, temperature, density, whatever, yeah.
yeah, so there's a wide range of hole densities where you have ferromagnetism, valley polarization.
Okay.
And
And
that's
within that, you get some turn, like plateau or something like that.
yes, that's correct.
Okay, but once you have time reversal symmetry broken and you have that Hamiltonian, it's kind of a classic, single Dirac cone situation, I guess, theoretically, isn't it? If I ignore like P, when you have like J dot sigma, your J has a structure, so which makes it more, I guess, Skyrmion crystal rather than uniform, like single Dirac cone situation.
I'm not sure exactly what you mean by Dirac cone in this
So
case.
like, I mean, like very classic way of thinking about integer quantum Hall effect, right?
Yes.
Way that I guess it's called type flux or something. You can get Dirac cones, and if you have single Dirac cone, you get a lot of things that kind of follow. I'm just trying to put what you're telling us in the context of what little I know.
When you're talking about Dirac cone, are you thinking from like how you get a turn band by opening a
Yeah,
Dirac gap in a
yeah.
topological way?
because your J dot sigma, if J was uniform, it would be like that, isn't it?
Not quite actually.
No?
Yeah. If J were uniform, I mean, if J were uniform in magnitude and direction, then it would just be basically a potential energy uniform offset.
Hmm.
But if J were uniform in magnitude but varying in orientation, then there would still be this emergent magnetic field. I mean, maybe it would help. Yeah, I mean, like if you look, you should think about these bands that you're getting here as you started
Yeah.
off with just a zone folded parabola going downwards. The zone folded parabola going downwards is what you get if you threw away this J, if J was 0.
Mhm.
But then all these band gaps opening are coming from, yeah, just Bragg scattering by the J, and that's giving you these bands that, well, the argument from this picture is that you should think about these bands as being adiabatically connected to Landau levels. They don't look like it so much from this plot because they're very dispersive and stuff, but it actually turns out that you should kind of think about like each one of these bands as being a Landau level that was like that was subjected to some modulation potential. And that modulation potential caused some bands to invert with each other, but it didn't cause some other band inversions. And so that some of those bands, like the first two in this case, are still adiabatically connected to Landau levels.
But why is it important that you think it as a Landau level? Like the Landau level as my quantum, introductory quantum level is
Yeah.
1, 2, 3, 4. It doesn't change sign. It doesn't go from -1 to -1. Your Chern numbers are very not like Landau level.
Yeah, well, I'm claiming that over here on the right-hand side at large twist angle, we're getting closer to Landau levels. I'm basically arguing that as you increase the twist angle, you're getting closer and closer to Landau levels. Because as you say, when you have Landau levels, it's all Chern 1, Chern 1, Chern 1, Chern 1. And off to infinity. And here I'm just saying, well, it's Chern 1 or Chern -1, Chern -1 plus 2. Okay, so it's not exactly like Landau levels, but at least with respect to the first two having the same Chern number, it is.
I'm just trying to understand why is that important? Like why is
Well,
this
yeah,
Landau
okay.
level so important? Yeah.
You'll see.
Yeah.
Yes.
Okay.
Oh, thank you for the question.
Well, thank you for
And-
being patient.
For sure. So Landau levels, yes. why are we interested in things being like Landau levels, at least in some approximate sense? Well, because as we talked about earlier, the lowest Landau level, there's a bunch of interesting phenomenology there in terms of the fractional quantum Hall states that we talked about earlier. But in contrast, actually, at half filling of the lowest Landau level, you don't get an incompressible fractional quantum Hall state. You actually get a gapless compressible state that is nonetheless not a Fermi liquid that we call a composite Fermi liquid. In contrast, but the energetics of different Landau levels are different. So in contrast, when you go to the first excited Landau level, one thing among several that are interesting that happens in the first excited Landau level is that when you go to half filling, in contrast to the lowest Landau level, you actually open up an energy gap. So you have an incompressible fractional quantum Hall state. And it's believed that this fractional quantum Hall state at half filling of the first excited Landau level has non-abelian anyons as its elementary excitations. So the focus of what I'm going to be talking about is if we want to realize a fractional quantum anomalous Hall state with non-abelian anyons, one possible strategy that we'll explore is to try to realize a band that in some sense looks like the first Landau level, the first excited Landau level. And so that's why these bands looking like Landau levels is it matters, because we want the second band in particular to look like the first excited Landau level. And yeah, I'm showing the band structure actually that I'm showing here is calculated according to this approximation, this adiabatic approximation where we derive this effective Hamiltonian that, as we said, we could think about as Landau levels plus fluctuations in the magnetic field and the scalar potential. And so the bands that you're seeing here are precisely the bands that emerge from those fluctuations. Okay. So yeah, let's talk about how this strategy is going to play out. So before we do that, I want to discuss a little bit of background information. So Landau levels have a very special and important property called particle hole symmetry. So we can define a particle hole conjugation operator. And yeah, I think, you hear the term particle hole conjugation all the time in different contexts, and it means different thing in different contexts. So in our context, this is what it means. We just have a block state creation operator, C dagger K. K is some crystal momentum, and there's some complex number in front of it. And then we conjugate it by this operator, and what that does is it complex conjugates the coefficient and sends the creation operator to an annihilation operator. So turns out that if you take any two-body interaction and project it to any Landau level, and you define the resulting Hamiltonian to be H sub NLL, and for the nth Landau level, then actually that Hamiltonian will commute with this particle hole conjugation operator at half filling. And that's actually a consequence of magnetic translation symmetry, continuous magnetic translation symmetry in Landau levels. But this property is very particular to Landau levels. It's not a generic property of block bands. So there's this fractional quantum Hall state that appears at half filling of the first excited Landau level. And one of the leading theoretical candidates for what the topological order of that state might be is given by this so-called Moreid-Pfaffian wave function, or at least that's a model wave function for the topological order. And it's written out here. And if maybe you're familiar with the Laughlin wave function, then one way to understand this is that this part of the wave function is the m equals 2 Laughlin wave function. So if we were talking about the, say, 1/3 lowest Landau level state, then this would be 3 here instead of 2. And the Pfaffian part, and then you get this additional Pfaffian factor, which is the Pfaffian of 1 over Zi minus Zj. And so this term actually gets bigger when two particles approach each other, and therefore has the interpretation of describing pairing between electrons, pairing in the superconducting sense. And actually, this Pfaffian part of the wave function is at least at large interparticle separations. If you take a px plus IPy spinless superconductor, this is what that wave function looks like in BCS theory, at least when when two particles, get far enough away from each other. So it's kind of like a pairing. There's kind of some pairing going on. And this Pfaffian state, it can actually be written as the exact ground state of a model Hamiltonian. And don't worry too much about the details of this equation. That's what that Hamiltonian is. The only thing that matters really for us is that it involves three particles. It's a three-particle interaction. And unlike three-particle interactions, or unlike two-particle interactions, three-particle interactions, when projected to a Landau level, actually don't commute with the particle conjugation operator. So this Pfaffian ground state, because it's an exact eigenstate of this operator that doesn't commute with particle hole conjugation, there's no reason to expect it to be particle hole symmetric. So if you take the Pfaffian and you act with the particle conjugation operator, you get a different state, which is defined as the anti-Pfaffian. But the point is that normally when people study fractional quantum Hall effect, what the problem that you're studying microscopically is a Coulomb interaction projected to a Landau level, which is a two-body interaction. But such a Hamiltonian cannot distinguish, even in principle, between the Pfaffian and anti-Pfaffian. For instance, if you evaluate the overlap of the Coulomb ground state, it will be the same between the Pfaffian and anti-Pfaffian. So if you will look at like some early numerical studies, for example, what's being shown here is this dashed dotted line is an overlap with the Pfaffian wave function that's called Moore-Reed paired here. And this black line is a Coulomb ground state overlap with the so-called symmetrized Pfaffian wave function, which is just an equal weight superposition of Pfaffian and anti-Pfaffian. And the x-axis here is just varying some Haldanean pseudopotential. So varying basically the form of a two-body interaction, just nudging it away from Coulomb in the first excited Landau level. And what you see here is that if you look at the overlap with the Pfaffian, then it's pretty high, 0.75, 0.8 or so. But actually, it gets a whole lot better when you take the overlap of the Coulomb ground state with the superposition of the Pfaffian and anti-Pfaffian. So what that's telling you is that when you do ED, the Coulomb ground state that you find is really a cat state, a superposition of Pfaffian and anti-Pfaffian. So it tells you that they're both pretty good candidates, but you have to do more work to figure out which one you're dealing with in a given system. Okay. So how are we going to do this? So we want to study the energetics of this first excited miniband here. We're going to half fill it. And we're going to make an approximation, which is we're going to assume that there are that the filling factor is 3 halves. So that means 3 holes for every 2 Moiré unit cells. And we're going to assume that those holes are all valley polarized. So they all live in the same valley. And we're also going to assume that we're not going to allow for any interband excitations. So we're going to assume that this lowest band is full, and we're not going to allow for any dynamics within that band. And where all the dynamics are going to be within this half full second band. And the Hamiltonian that you get when you do that is just more or less a standard band projected Hamiltonian. You have a one-body term with a band dispersion, epsilon tilde, and you have a two-body interaction in terms of the projected density operators. But this epsilon tilde, it's not just the bare non-interacting dispersion of the second band. That would be what I'm calling epsilon of K here. There's actually an additional contribution that I'm calling sigma Hartree-Fock, the Hartree-Fock self-energy, that is basically just accounting for the fact that there are actually some holes already occupying this full lowest band, and those interact with the holes that are in this partially occupied band. So you have to account for it. And I just want to remark that I said I made the assumption that we're at 3 halves, n equals 3 halves, and all the holes live in the same valley. If we were to consider the case of 5 halves and assume that basically the first miniband in both valleys is full and the second miniband in one of the valleys is half full, then the only difference in the calculation would just be to change the form of this Hartree-Fock self-energy.
Aiden?
Yes.
So I don't know the estimates from the continuum model or DFT for what the actual energy scales are, but after you account for the Hartree-corrected normalization, is the interaction strength smaller than the gap to the remote band, the one that you label as empty?
Yeah, so good question. No. Yeah, interactions, that's a problem with I mean that's a generic issue when doing ED in these Moire systems. Uh there's no separation of energy scales, and so the interactions are generically not small compared to the band gap
But you're
in
still
these
going
systems.
to just work with the projected model.
Yeah, that's true. So it's an approximation.
Okay.
Yeah. Yes. And it's not quantitatively, it's not, I mean, it's not quantitatively controlled because there's no separation of energy scales.
So the importance of having this Hartree-Fock self-energy, is it because your bands are not flat? Otherwise,
Well,
it's just a number.
So well, it depends on K.
Mhm.
So yeah, so it changes the band dispersion. And actually, naively, you might say, you might expect that it would only hurt.
To have it, you mean?
Yeah, one might naively expect that, well, if I neglect the Hartree-Fock self-energy for whatever reason, then that would only make it more likely to stabilize some correlated ground state, like a non-abelian FCI. Surprisingly, maybe it turns out not to be the case. Actually, it turns out that it helps. And I know that's something that we found and other groups who looked at similar problems also found.
Aiden, another quick question. So
Yeah.
for the projectors, do you use the
Yes.
block wave functions of the non-Bayer band structures, or do you renormalize? Like, how much of the block wave functions renormalized?
So yeah, at our level of approximation, the block wave function is the non-interacting block wave function. So one thing that someone could imagine doing is doing a self-consistent Hartree-Fock calculation at some filling factor, say n equals 1, then taking the self-consistent Hartree-Fock bands, the renormalized self-consistent Hartree-Fock bands, and doing a calculation with those. That's not what we did in this case. We just took into account the effect on the block state energies, basically.
But do you know
But
if the wave functions are renormalized enough for the Bayer curvature distribution to change significantly, or is that a small effect?
so I mean, I would expect it in general to be non-negligibly small. But yeah, like it wouldn't be so small as to like be just numerically negligible. But I mean, what I would expect it to do is basically just to leading order shift things around in twist angle, where things are most stable in twist angle. And so we didn't look at that effect, but other groups who did similar things did look at that effect that you're describing, and they still found non-abelian FCI for certain twist angles. Yeah. But what I should say is that all this procedure is still variational. Even if it's not perturbatively controlled with respect to any separation of energy scales, it's still variational.
And just to confirm, Aiden, sorry, maybe it's literally the same question the Banjan asked. So the quantum geometry and the Bayer curvature distribution are literally the same as the non-interacting.
Yes. Yes. At our level of approximation, that's true. Yeah. Okay. So now we can do the calculation, and basically one way to diagnose the nature of, I guess, really any state in an exact diagonalization calculation is just to compare it to a case that you understand. And so a case that we understand, if we want to ask the question, does our ED ground state, does it correspond to, say, a Pfaffian? Does it have the topological order of a Pfaffian? The first thing one should do, in my opinion, is just compare it with what does ED look like for that known case. So this is what ED looks like for that known case, where we take the exact parent Hamiltonian that had the three-body interaction that I talked about earlier. And what we see is for this particular system size, we're working on a torus, and this is for 13 electrons. What we see is that we have two ground states with these center of mass quantum numbers. That's just what this x-axis is, center of mass momentum. We get two ground states with these particular momenta. And if we do ED, as I just described, for this adiabatic model of twisted MoTe2. Adiabatic model meaning where we made this approximation where we projected onto alignment with the layered Zeeman field. And I'll address more about what happens if you don't do that later, but that's the model that we're working with for now. You get ground states with the same degeneracy and center of mass quantum numbers. And another thing that you expect to see is that actually for this Pfaffian and anti-Pfaffian states, there's an even odd effect in the ground state degeneracy. In terms of, an even odd effect in terms of fermion number, how many particles you have in your system. The ground state degeneracy should be 2 when you have an odd number of electrons and 6 when you have an even number of electrons. That's unique to these non-abelian fractional quantum Hall states. The abelian ones, they don't exhibit any even odd effect. And what we see is that for a system size with an even number of particles, we also have matching between the ground state degeneracy and the center of mass quantum numbers. So those are just 2 particular choices of finite system size. We did it for many, and you see that the same trend continues. So yeah, it could be the case coincidentally that maybe for one system size, the numbers happen to be the same, but that's not the case. It's consistent. And another thing that I should say is that it's not trivial that you just get that the ground states exist in these particular center of mass momentum sectors. For instance, you could imagine that maybe a competing state would be a composite Fermi liquid. But when you do ED on a finite size system for a composite Fermi liquid, you find that those ground states have different quantum numbers. So it's a powerful way to distinguish between different possibilities. Furthermore, another numerical experiment that we can do is to study how the spectrum, the many-body spectrum, evolves under insertion of magnetic flux through a handle of the torus, and that's what I'm showing here. So I've highlighted the ground states, of which there are 6 for this system size in red, and I'm going from 0 to 1 flux quantum through one of the handles through the torus, and you see that those ground states flow among themselves, but more importantly, they don't cross with any higher levels. So that gap, it doesn't close as a function of flux insertion, which provides some evidence that it's not just a finite size gap, that it's an actual feature that should be there in the thermodynamic limit. Of course, at finite size, every Hamiltonian is gapped. So it's just showing that it's not gapped for that in that trivial sense. And another thing that you can look at is the momentum distribution function, which is just saying, what are the occupation numbers of the different block states in my many-body ground state? In this case, we're looking at the occupation numbers in the second miniband, and you see that those are uniform. That would be in contrast to what you'd get if you had a Fermi liquid, where you'd see that there's some finite size Fermi surface across which the occupation goes from near 0 to near 1, or at least has a discontinuous jump. So I just want to remark that, to my knowledge, this is the first numerical demonstration of a non-abelian FCI with a Coulomb interaction, without making any sort of modifications to a Coulomb interaction. For example, by adding some short-range attraction in by hand, or adding a 3-body interaction, which is what people have done in previous studies. And I think that the main difference between our model here and previous studies is that we're working with a band that looks like the first Landau level, whereas most models that people had been working with before, they're working with churn bands that look more like the lowest Landau level. Okay, so there's
question.
Yes.
So if I made a gross approximation and just flatten the band or something.
Yes.
If I just made it really just, first Landau level, I wouldn't have had to do a whole lot of work, right? So in a way, you have a dispersion, your E of K was not flat, and as a result, your high-triple self-energy was also important. And
Yes.
there was all these additional richness, which turned it into a lot of work for hardworking graduate student. But in terms of like the, 140 character synopsis, let's say, it's the same story as, like, you're getting what you would get if you had first Landau level and Coulomb interaction. Is that right?
Mostly yes, except for one caveat that I'm about to address.
Okay.
But I would also add that to some extent, the same thing could be said for about most fractional turn insulators, most numerical
I
studies.
say the same thing to every fractional.
Yeah. So, but the difference here is actually that our Hamiltonian does not have particle hole symmetry.
Mm-hmm.
So that will actually allow us to distinguish between Pfaffian and anti-Pfaffian at the level of the band projected Hamiltonian.
But if you have,
So how
if
can
I
you do
have
that?
if I just have a Landau level, if I go to the
Yeah.
first Landau level, I also don't have particle hole symmetry, right?
Not in actuality, but usually at the level of theory you do, because usually we don't take into account Landau level mixing. And even if you do, which various numerical studies have attempted to do, it's actually been quite challenging to sort of do that properly for various reasons.
I guess that's where we get to like DMRG and stuff like that, all the.
Yes, but even then,
Yeah.
there is in the literature, there's been back and forth over the years about what is the effect of Landau level mixing. Does it sway things more towards Pfaffian or anti-Pfaffian?
Right, I think the part of the long debate was really fueled by the fact that, all the theories, one way or another, various ways of trying to address all the right things, give you one prediction, and the experiment, maybe one or two experiment that's available, gives a resounding opposite result, which kind of fueled the debate.
Yeah.
So there is no success story. There is no history of success in predicting Pfaffian or anti-Pfaffian and having it compare favorably or productively with experiment. To my knowledge.
Yeah, I mean, I think I would agree with that. Yeah, based on my understanding of the situation. But I mean, the hope is that in our case, the breaking of the balance between Pfaffian and anti-Pfaffian
is much more severe. So
will be more severe and therefore easier to identify in numerics. But then, of course, the caveat is that there's probably more uncertainty in the model. I mean, there's more uncertainty in the relationship between our Hamiltonian and the material than there is in the Hamiltonian and our numerical results. I would say. Whereas in the conventional quantum Hall case, I mean, there's very good certainty about the Hamiltonian there, I would say.
Yeah,
whereas in our case,
only one Hamiltonian.
Yeah.
Modulo issues of disorder, which might be important for interpreting.
Yes.
The experiment.
That's true.
Yeah, I agree with that. That's true. But I think I don't have a ton of time left, so maybe I'll just say there's a mapping that one can do to calculate things like overlaps. And we did that, and I'm happy to answer questions about it. And when we did that, we basically found, I'm showing you several system sizes here as a function of twist angle. In blue is the ground state overlap with Pfaffian, and in black is the ground state overlap with anti-Pfaffian for a given system size. And what you see is that in this range of twist angles around 2.5 degrees, both the Pfaffian and anti-Pfaffian overlap become sizable, and they're not, they're both sizable, but the Pfaffian consistently exceeds the overlap with the anti-Pfaffian across all system sizes studied. So that provides some evidence that our Hamiltonian is more likely to realize Pfaffian topological order in the thermodynamic limit. Okay. So
Sorry, question?
Yeah.
Do you mind going back maybe 2 slides? And
yes.
Relevant, maybe, okay, probably more, where you have the 6-fold degeneracy and 2-fold degeneracy stuff. Sorry, a little bit more. Yeah, here. So yeah,
Yeah.
that's exactly the thing that I'm looking at. So for certain system size, the 6-fold degeneracy are really great, one of them at least.
Yes.
But other system size, it's right, like it, there's a lot of energy variation and whatnot. So
Yeah.
do you know why, or do you know what system size would help you get the degeneracy like right, or
So,
get them really degenerate, and also related to the overlap that you're doing? I know you're skipping a lot of details, but I mean, there are so many states to pick to do the overlap on, and then they have different energy and whatnot. So did you go for the
yeah.
best overlap, or it's some kind of average overlap?
Yeah, I mean, it's the total overlap. So you have a model wave function Hilbert space let's say it's 6-dimensional.
Yeah.
Then you can just take your Coulomb ground state and then project it onto that 6-dimensional vector space and then calculate the squared amplitude of that,
Okay,
for
I
example.
see.
That's basically what we did. Yeah. So that you don't have to make a choice about which one to take the overlap with. It's
Sure.
independent.
Okay.
And then in terms of the splitting, I would say I agree with what you say. There is splitting. I believe it's just a finite size effect. And in particular, it's less severe on certain clusters where, so for example, there's a big finite size splitting for this cluster.
Yeah.
And one possible interpretation of that might be, well, in this case, you have 4 states living in the same momentum sector, and
Okay.
they're coupled by, yeah. So basically, they're allowed to level repel with each other, and so they lead to more splitting. Whereas in clusters where you have fewer states in a given momentum sector, there's less level repulsion that would vanish in the thermodynamic limit.
All right. Thank you.
Yeah, thanks for the question. Okay, so basically, these are some single particle properties of the second miniband. I'll just say that there's a magic angle sort of behavior, where as a function of twist angle, the bandwidth has a minimum, a cusp minimum. That's sort of around the regime where we see this state is stable. And also, you can directly quantify within our model how much this band looks like the first Landau level, because we actually, when we compute the block states in our bands, we're actually computing them numerically as a linear combination of Landau level states. So you can just directly look at what is the average weight of all the block states in that band with the corresponding magnetic block state in the first Landau level. And we call that the Landau level weight, and it's very high. So in that sense, it would be a number between 0 and 1, and it's a bit more than 0.9, say in this case. So it is, in that sense, very much like the first excited Landau level. Other groups did similar modeling to us. They were asking a similar question, but yeah, some groups did their own first principles calculations in a range of twist angles around 2 degrees. And what they found is that you actually get a sequence of Chern bands that have the same, not just the first 2, but several Chern bands in a row that have the same Chern number, and in that sense look like Landau levels. And they also did similar many-body calculations, and also found FCIs at half filling. Okay. So I won't take, maybe I'll just, try to get through this within just a few minutes. So what else can happen energetically in this half-filled second miniband? So far, we really focused on a range just around 2.5 degrees or so, where the many-body spectrum looked like this. But what I'm showing you here is the many-body energy spectrum for a particular system size in a broader range of twist angles. And what you see here is that in this window of twist angles around 2.5 degrees, there's an energy gap that in this case, there's a 6-fold approximate ground state degeneracy in this region. But then outside of this region, there's some level crossing among the ground states and excited states that corresponds to some phase transition. And so what's going on in these other regions? Well, actually what's going on is that you get a crystal, an electronic crystal on the lattice, and the translation symmetry breaking pattern of that crystal actually it corresponds to a 2x2 enlarged unit cell. So you're at half filling, and you spontaneously quadruple the unit cell. And you can look at for instance, a projected structure factor. And the way that shows up is through Bragg peaks or finite size analogs of Bragg peaks. And when you see that in this case, the radius of these dots here corresponds to the magnitude of the structure factor at that momentum point. And you see that there are Bragg peaks basically at the endpoints or the midway points of the Moray-Brillouin zone, which is the momentum space version of saying that you quadruple your unit cell. And the size of these Bragg peaks grows with system size, which if that continues indefinitely, then that's the definition of long-range orders. So that's some numerical evidence for translation symmetry breaking. That's a bit of a technical point. These crystals, depending on the twist angle, they actually can have different Chern numbers. So I'm showing you here the calculated many-body Chern number for different twist angles. And this is within the adiabatic model. So it's the same basic Hamiltonian that we looked at earlier, except just changing the twist angle. And okay, at 2.5 degrees, you actually get a total Chern number of 3/2. That's just the Chern number that you expect for the fractional Chern insulator, which it's fractional. But at other twist angles, when you have a crystal, that's a gap state, and it can, in general, will have some integer Chern number. And depending on the twist angle, it can actually be 0, 2, or 1. Now, there's something peculiar about when that Chern number gets to be 0, which I'll talk about now. So all the numerical results that I showed you so far were to do with the adiabatic model, where we made this approximation where we we got the emergent magnetic field, but we can also just take the original Hamiltonian without making that approximation. And when we do that, actually in the region of twist angles where the adiabatic model gave us a fractional Chern insulator, we don't get a fractional Chern insulator, at least for the model parameters that we used. And I can talk, if people are interested, I can say more about, what different first principles calculations have to say on that matter. But at least for the model parameters that we were using, we didn't get a fractional Chern insulator. And instead you get a big region where you have a crystal, just like we were talking about earlier, and it's Chern 0, which, you do a many-body Chern number calculation, and over this range of twist angles where you have this gap in the ED spectrum here, you get Chern 0. But there's something very weird. Even though it's Chern 0, why do we call it anti-topological crystal? Well, it's kind of weird that it's Chern 0. Because actually what's happening is that, as we said earlier, you're in a regime where you're half filling the second miniband in a given valley. But that miniband has the same Chern number as the full first miniband. So to get a total Chern number of 0, the crystal that's being formed in the second miniband has to have opposite Chern number to the band that it lives in order to cancel out the Chern number coming from the full first band. So in that sense, it's anti-topological because
this reasoning, or is this I'm a little confused because I can think about a crystal without thinking about kinetic energy at all, right? I can get a crystal by just thinking about long range interaction. Then I wouldn't have Chern number because I don't have band. I can just get a crystal without ever referencing bands. So my crystal that I arrived that way would not know that it is failing to be a topological something. It was just doing a normal thing. Is this what's wrong with that picture?
In principle, there's nothing wrong with that picture, but actually, the difference here is that in these ED calculations, which I'm showing you right here, we're making the same approximation that we did earlier, which is basically not to allow for interband excitations. So in that sense, we're forcing a part of the many-body wave function to still be a Chern insulator, which is the full first miniband. So in that sense, our many-body wave function knows in a sense, there's part of the wave function that is still a Chern insulator, but there's another part that's a Chern insulator with the opposite Chern number.
But isn't that kind of artificial way to reason? This seems to be more a matter of philosophy rather than so here's a test. You can just reduce your kinetic energy right?
Yeah,
You can take your calculation, go to the limit where your kinetic energy is vanishing.
yes,
Do you see anything change to your crystal? My guess is, so either there is some sort of transition from
Yeah.
your anti-topological crystal, which has this knowledge of the topological band and somehow chooses to do something rebellious,
yes.
versus plain old classical
So
physics
here's the
of
difference.
repulsive interaction. Is there a transition or something different?
Yes, there's a difference in the translation symmetry. Because
Okay.
actually, so suppose we had a classical Wigner crystal, like
Mhm.
as far as is what you're talking about.
Yep.
In that
yep.
case, we would have 1 electron per unit cell
Mhm.
of that crystal. In our case, we actually have 6 electrons per unit cell of the crystal. And that wouldn't be the case if kinetic in the limit that we took kinetic energy go to 0. That would not be true in the classical limit. So that's the sense in which bands are still known about.
But you
There's
said the
actually
unit
6 electrons per
cells.
unit cell of the crystal.
Okay. And
Because oh, so, yeah, did you want to
I
ask
guess,
something?
I mean, I think of a crystal as, unless that I have additional quantum number, right? My crystal is
Mhm.
defined by what is the space occupied by 1 electron. So I don't quite understand I mean, is it just because you have additional quantum numbers? You're 6?
I guess, yeah, I just mean energetically, the ground state of the system is such that it has 6 electrons per unit cell. Which would definitely not be the case in the classical limit. That would just never be energetically preferred. But because, I mean, it's a balance between kinetic energy and interaction energy considerations that's leading to that being the case. Because basically this state doesn't want to disintegrate the lowest band. And speaking loosely, right? It's still energetically there's a large energy cost to break up that lowest band. Energetically, it's not doing that because it doesn't, there's a band gap that's still there in a sense. And so therefore it's kind of forming the electrons in the second band are forming a crystal, but without profoundly perturbing the electrons in the full lowest band.
So you're saying with the way you organize the model, you're really staying band projected.
Well, actually, I mean, in the ED calculation, that's what we did. But what I'm showing on this slide is actually basically you have to do that in ED.
It's supposed to be
just
just
to
a
make,
full Hamiltonian, right? No projection, right?
yeah, in Hartree-Fock, we're making no approximations beyond the Hartree-Fock approximation. So in this calculation that I'm showing you here, there's no band projection. All bands are included. There's a UV cutoff in momentum space, but everything is numerically converged with respect to that cutoff. And we get the same conclusion.
Wait, Aiden, I'm now confused. I mean, this anti-topological crystal, I thought you obtained using ED for the band projected Hamiltonian.
No.
Yes, that's correct.
Okay.
But so we did that. And then basically another thing that we did was just to do a self-consistent Hartree-Fock calculation and see without band projection and see if we got the same answer. And we did both calculations and we arrived at the same answer.
The answers are the same?
Well, they're the same in the sense that the ground states that both methods gave us have the same translation symmetry breaking pattern and the same many-body Chern number.
Okay. Which is 0.
Which is 0. Chern number is 0.
Okay.
But within the Hartree-Fock approximation, there's still a sense in which I can say that the underlying MoTe bands have Chern numbers of the same number. That both have the same Chern number. So when you have translation symmetry breaking in Hartree-Fock calculation, you break up your Moire band into subbands just because of the formation of the charge density wave. And because we have a quadrupled unit cell here, each Moire band is actually folding into 4 subbands. And so and this band plot that I'm showing here, yeah, unfortunately there's not really a great way to make this band plot. But basically you see this spaghetti down here, and there are kind of 4 bands. That's actually just the lowest Moire band folded in on itself 4 times. And then you see up here that there's 2 sets of 2 bands. These, which are 4 bands in total, and those you should think about as corresponding to what was originally the second Moire band. And now you have a gap opening between the first of these 2 and the second of them. And that's the gap opening at half filling of the second Moire band due to the formation of the charge density wave. And basically, I can look at this manifold of, in this case, 8 bands, in the window that I'm indicating, in the energy window that I'm indicating. And these 8 subbands are actually the subbands of the first 2 Moire bands, because it's 2 times 4 because the unit cell is quadrupled. And actually the Chern number of that manifold of 8 subbands is 2, which is precisely saying that the first 2 Moire bands have the same sign Chern number. However, if I sum over all the Chern numbers of these subbands up to here, up to the Fermi level, which gives me the many-body Chern number of the self-consistent ground state, that's 0. So that's the sense in which it's still an anti-topological crystal, and it still knows about it's still somewhat meaningful to talk about the Chern number of the bands. Yeah, please ask questions if people are interested in understanding that better, because that could potentially be confusing. But yeah, in any case, the Hartree-Fock calculation gives the same answer about what is another possible ground state besides the fractional Chern insulator as the band projected ED. Okay, so yeah, that's the end of my talk. I basically talked about our study of the possibility of a non-abelian fractional Chern insulator at half filling of the second band in twisted MoTe2. And then we studied the broader phase diagram as a function of twist angle, and also looking at the continuum model without making the adiabatic approximation. And what we found there is an electronic crystal with a quadrupled unit cell that, despite being at half filling of the second miniband that has the same Chern number as the first miniband, ends up being in a state where of Chern 0 in the ground state. So there's a sense in which the formation of the crystal is canceling out the topology of the underlying bands. And so that's why we gave it the name anti-topological crystal. So thank you for listening.
All right, thanks. So we've had a bit of questions, but if there's any pressing ones, maybe we can answer them. Yeah.
So Aiden, I have a question related to the first part.
Yes.
Actually, 2 related questions. If it's a long discussion, then maybe we should take it offline. But you did mention, like, if the non-abelian FCI state is only stabilized in a regime where you realize the ideal phase condition, or if it's robust over a more extended region. And if so, I noticed you just quickly flashed results for the projected structure factor. So,
Yeah.
like, what's the leading Q dependence of S bar of Q?
You're talking about here?
Yes, but at small Q.
Yeah.
0.
Yeah. We did not look into that. We did not look into. Yeah, I know exactly why you're asking. Yes. Yeah, we haven't looked into that.
Maybe we can take this, you talk about it some other time.
Sure. Yeah. But yeah, that's an interesting question.
Thanks.
Other questions?
So I have a question. If I
Yes.
take Haldane model,
Yes.
and and introduce interaction,
Hmm.
I can go between at partial filling, fractional filling. I can
Yes.
go between fractional, I don't know, fractional, I guess FCI and charge order state.
Yeah.
And the charge order state will have C equal to 0.
Yes, but so that situation is different from what I'm calling the anti-topological crystal because well, suppose that you're in the Haldane model and you're at 1 electron per every 3 unit cells. Well, in
Right.
that case, you're only starting in there's only one, there's no valence band. Like there's no full band below the Fermi level.
Mhm.
Um,
So you're saying your emptiness has to do with that there is a full band underneath? Is
yeah,
that
there's a
where
full
the
band
emptiness
underneath.
comes?
Yes. And well, so there are 2 ingredients. There's the fact that, okay, I'm in a churn band. There's a full churn band underneath. And the churn band that I'm in has the same signed churn number as that full churn band that's underneath.
Okay. Same sign.
Yes. So that couldn't that this and there would be no analogous situation to this in the Haldane model because you would never have 2 bands that have the same signed churn number in the Haldane model.
Right, right. No, yeah, so okay. But in your designation of emptiness, is it the fact that there is a full band that you don't really ever think about? Or is it the fact that you are partially filling a particular band of churn number? Where is your emptiness designation coming from? Or are you saying you need both of them and they have to have the same sign? I'm just trying to understand the reasoning.
Yeah, yeah.
The
So
way
I
you
mean,
guys are thinking about this.
it is more of like a qualitative description of what's going on. It's not a symmetry or topological distinction. I mean, well, it's a symmetry distinction between what would be the Wigner crystal at this given density, because as we discussed earlier, that would have a different translation symmetry breaking pattern. But at the end of the day, it's still a topologically trivial state. But the reasoning behind anti is to say that you have a churn insulating background. That's the full first band. And you're forming a crystal in the second band. And suppose that we say that the first 2 moire bands, they both have churn number 1. Then the crystal that you're forming in the second band, well, first of all, it basically has churn number -1. So it has the opposite churn number as the churn number of its underlying band, and the opposite churn number of the full band below it. And so it's canceling out the topology of the full band below it. So that's what the anti means. It's that you kind of have like 2 topological things that come together and are making a trivial thing. But it's unusual in the following sense. In Landau levels, you have this phenomenon that people oftentimes call the reentrant quantum Hall effect, where you'll basically be between 2 integer filling factors, and you'll be at a fractional filling at some high Landau level. But then you'll have a range of magnetic field where your Hall conductance is quantized to the nearest integer. And the way to think about that is, well, you have a bunch of full Landau levels, and then you have just a trivial crystal that's forming within the Landau level at the Fermi level. So that's, but our case is different from that because the crystal that's being formed in the band at the Fermi level, it itself is not trivial because it's canceling out the topology of the background. So, and that, yeah, it's distinct from that, from like the reentrant quantum Hall effect, for instance. And it's distinct from any other crystals that have been studied in partially filled churn bands before, because most of them aren't in this situation where we have multiple churn bands.
Maybe you should make it NT-square, because you seem to be using two bands having finite churn number for your argument. Your filled band and the
Yeah.
band that you're partially filling.
Yeah, I mean, I hear your point. Yeah, the anti is kind of pointing towards both of those things, which are, yeah, they're conceptually distinct. Yeah.
All right, so let's thank Hayden again.
Yeah, thanks everyone. Thank you for listening.